Hi, everybody. How you doing? Welcome to the Virtual Night Sky. This is our opening program of the 2022 year. So for those of you that have been following us in the past, you know that we do this every other Wednesday. We went right up until December. In early December, we had a program of December the 1st, and we took a little break, for the holidays. We sort of all had things to do. We thought people would be interested in other things, but we promised to come back on January 12th. And so here we are. We're going to continue this every other Wednesday until everybody gets tired of us, which I hope is a long, long time from now. I want to welcome all the new people. We have really quite a crowd today. So thank you very much for joining us. And we always understand that we have some people that kind of follow along and we've seen you before, and we always have new people. And so as a producer and as the presenters, what we do is we try to put together some reminders, some old stuff to bring everybody kind of up to speed, and always try to introduce some new things, some new ideas, and some new things to look at. This year, we're actually going to start out with a couple of series, and one of them is what I call How the Sky Works. So if you want, these are just a handful of little basics. We're going to cover them over the first 5 episodes. Tonight, we're going to start with stars. What is more basic than stars? Why we see the stars we do, where we do. We're going to cover that. And then also tonight, Alicia is going to give you an assignment. I'm going to show you some things that are going on in your night sky right now. And so she'll follow me and kind of give you some things to look at, some things to go find in the night sky. We also have a James Webb Space Telescope update. And I hope some of you actually watched the launch, or certainly it was in the news. I hope you're aware that that amazing telescope was launched off the Earth. It is now in space. And so Alex is going to give us an update. We also have some resources and some things that we do every week. And then I'm going to finish with the beginning of another series. It's a project, or I'll call the 5 things. And I'll explain it when we get there, but we're going to cover each one of those, the first 5 things in the first 5 episodes. So tonight we're going to kind of cover thing number 1, and I'll explain when we get there what you're supposed to do with that. So I know we have a lot of teachers. I want to welcome you tonight. We sent out this particular announcement to a lot of things, and so we are looking for ways to engage with your students in the classroom. We thought that we were going to be able to really, right off the bat, first part of the spring here, start having school field trips back on campus and back in our building. And lo and behold, COVID, as you all know, raised its ugly head again in another variation. And so we're going to hold off on that for a little bit. But we do have ways to get into the classroom virtually. We're training a new rack of students that we're training to start to be able to be presenters and all that stuff. So we look forward to working with our teachers through this semester a bit more than we have in the past. And we know springtime is when you guys like to work with us. And so let's find ways to do that and welcome teachers. For all the old people, or not, I shouldn't say old people, for all the people that are seasoned and have been with us for a while, welcome back. And I hope you enjoy another annual series of virtual night skies. This program is done in a webinar format, and that means that we turn off the chat. We just don't do that. It gets kind of busy and it gets out of control, and so we just don't do chat. But you can communicate with us, and so there is a question and answer button on your screen. Go ahead and press that, and just sort of, if you have a comment, if you have a question, if anything sort of that we're talking about tonight that you need like clarification, you want to know a little bit more about, we follow that all the way through the program, and Alex and Alicia will be in the background. They answer some of those questions as we go, and then we bring some of those questions forward to breaks. And so we take a couple of breaks and kind of stop and take a moment to sort of answer some of those questions. But it's a really good way to communicate with us and tell us you're here, and tell us what you think about the program as we go along. So do that. There is a closed captioning. We usually run that. We like to sort of just, we use it because we post these things later. They're easy to repost, but you can turn it off if you want. So you're in charge of that. How your screen looks is up to you. We like to sort of, if you sort of make the main presentation screen big and have the gallery or some of the other little things in the side, that's how most people do it. And you can either use captioning or not. It's your choice. And I think those are the cleanup things. Kim will be sending you after this event in the following days, kind of a little follow up and all that stuff. And included in that is a survey. And if you'd like to take that survey seriously, kind of give us some thoughts as we go along. We're always trying to improve the program, and we're always trying to look for things that you're interested in so that we can fit them in. On the team here, I'm just going to introduce everybody, and then we'll get started. Meg Hufford is on the line. Meg and I are the partners at ASU campus that have led the program where we have public outreach that comes to us. And so during COVID, things have been a little weird because you're not coming to us, but we found other ways to do this, including this particular program. But Meg and I have worked together for a long time. She's with us to kind of watch things and help things along. Kim Baptista is what I call the producer. She's the one that kind of keeps this thing organized and sends out the communications to you. She sends out the notices and all of that stuff. And so Kim is on board. She's the one that probably is your most communication with us. So when you link on, when you register, she's the one that follows that and makes that happen. Alicia Hyatt is a former student and now a part-time staff member, and she's with us tonight. You'll hear from her. She's actually going to give you a little bit of the night tour and some things to look at in the night sky. And Alex Blanche has been a student in our program for a long time. I guess Alex is I'm going to say a junior. You can correct me later, Alex, if you're not. So we have him for another year, and he's been with this program since the very, very beginning. And so we really appreciate having him aboard, and you'll hear from him a little bit later. Oh, that's correct. I see. Yes, oh, good. Thank you. All right. With all that said, unless somebody's going to try to stop me, I'm actually going to share my screen, and I just want to just show you some of the technology we use, and we're going to have a really good conversation about how the sky works. And actually, I'm going to add to that a little piece. I'm going to suggest this: not only the sky works, but what's observable. What do we get to see, and how does that happen? And so, oops, I just shared exactly this. Start off the bat, I shared exactly the wrong screen, so let me do that again. Now I can't find it. Hang on a second. I'm sorry about that, folks. Just hang on one quick second here. I can kind of get this going. I did a little change just before the show, and here it is. Here it is. Okay, that should be what you're seeing. So this is actually a piece of art that sort of shows up every once in a while. It represents sort of the medieval kind of sky view. It really can't be cited because actually I did a little research. We don't actually know who produced this or specifically when it was produced, but I love the way it sort of like tells a story of a dome over your heads. We're going to talk about this, right? Those stars, the moon with its phases, the sun. Over the course of the next several weeks, we're going to kind of follow all of those and talk about how they work. But look how this guy is kind of peering through the dome. He knows there's something else out there. He's looking past it into space. And this is often used for astrology things and all kinds of different ways to sort of think about the sky in all kinds of in ways. And that's really part of our cultural heritage, how we've come to learn about the sky, how we observe, what we can see, what we've come to know scientifically along the way over the last several hundred years. But there's still something about just you being outside, looking up at the sky that instills wonder, and I hope it still does that for you. And it's really one of the things we're going to try to do is kind of recreate that original excitement of what we see and when we see it and how we see it. So I'm going to kind of just get us out there. We use a program, piece of technology at the ASU campus, and it's called SkyScan. This particular program is called Digital Sky 2, and it's a very clever way of using a planetarium engine to put all of the data available, we need to sort of do simulations and fly around. And I just wanted to remind us that we're stuck here on this Earth. This is where we see the sky from. This is our platform, if you want, as we're flying through space. This is also real time, so if I flip around over here, I can show you where you are. The sun just set fairly recently. That's Phoenix, by the way. I always wondered if we got everybody to flash their porch lights on and off really fast right now, whether we'd see it. I suppose not. But anyway, that's the big Phoenix metropolitan area. And so we always have to remember that our view is determined by a little bit about where we are on Earth, but more about what the Earth is doing. Earth is moving through space, and Earth is orbiting the sun and spinning around. And we're going to look at that really closely for a moment. Let's just get this scene set up a little better. I'm going to add an orbit to the Earth, and I'm going to kind of just set up a scene here so we can see everything where it is. There's the sun, there's the Earth. We'll get these things organized together, and voila. I have the Earth blown up really, really big. So this isn't the Earth-Sun relationship in actual size, but it is where it is. And I'm gonna start this little machine moving a little bit. I'm just gonna kind of start spinning the Earth. And so at nighttime, of course, we're over here. You saw we were here, the sun had set. We're moving kind of through the night. At midnight, we're looking straight out in this particular direction. And here we are again in the middle of the day. We turn our face towards the sun, away from the sun, and towards the sun. You get that part. It's the spin of the Earth and its relation to the sun that gives us our day. That 24-hour day, that thing that we're sort of attached to now, how we manage our lives and run our clock, it is very, very specifically the movement, the spin of the Earth, sun to sun. And the average time that it takes to do that is 24 hours. And so that's how we mark our day. But there's something else going on. The sun isn't, the Earth isn't only spinning. The Earth is also moving around the sun in an orbit. Let me speed it up a little bit. I hope you guys don't get dizzy. Is this all right? And so you're noticing on the screen now is that the Earth is moving in this direction. So every day, not only does it spin around once, but it also moves in location. And you can see now our night sky. If you kind of look at this direction over in this way, we're actually looking out towards a different part of the sky than we were when we started this movement. Remember back today, we were here and our night sky view was over on this side. Now we're almost 2 or going on 3 months later, and we have a totally different sky, totally different night sky. Let me just keep it going for a second. I want to talk to you a little bit about why this is significant. Not only do we get our day from the spin of the Earth and the movement of the spin of the Earth and the relationship with the sun, but we also get our annular calendar for this. So essentially, as we move around the sun, as you know, it changes its position in the sky relative to us, and also the part of the Earth that is sort of tilted towards the sun or away from the sun starts our seasons. So all of this is locked in. These two movements, the spin and the orbit, is how we set up our calendars, it's how we regulate our time, it's how we do everything. So if this means the seasons are predictable and they have an annual cycle all the way through, as you know that, right? There's a planting season on one side of this orbit. There's a harvesting season at one part of this orbit. There's a, store your food and make it through winter on one side of your orbit. And then there is spring and that time. And it's absolutely rock solid regular. And everything about how we've set up our lives and our calendar, everything, how many things in your life are annual? It's the annual start of the school year. Your birthday is annual. The day our taxes are due, that's annual. Your car registration is annual. All of those things happen. And so if you can remember those annual cycles, think of those annual milestones that are important in your life. And at the end of the program, I'm going to invite you to sort of take a little timestamp and find a place in the night sky that makes that make sense to you. So that's really the first thing we're going to talk about in our 5 things. But going through this, I just wanted to make sure that we understand this motion, understand how this works. One more thing I'm going to talk about is that as the Earth spins, you can imagine, it's not hard to understand how a 24-hour day comes about. But we also have a little thing we call star time or sidereal time. So our clocks, your clock, your alarm clock, everything you do, your hours of the day are based on the sun. So that's called solar time. And that's what you're used to. There's also a star time. Sidereal time is the name for it. And it's 4 minutes shorter than a regular day. What that means is as we spin around, right, we get back to the same position against the background stars just a little tiny bit before we get back into a position facing the sun. Not very much, 4 minutes. But over the course of a whole year, those 4 minutes every day, the difference between star time and sun time, solar time and sidereal time, the difference between those things add up to a full 24-hour day. And so scientists and astronomers understand this relationship. We use sidereal time to sort of like map the way the sky works, the way the stars work, what stars are going to be available to you is all on that sidereal clock, not the solar clock. And the two are interacting with each other, especially in this scene. Let me just restore this a little bit. I'm going to get rid of the Earth's orbit there. We're going to land ourselves back on Earth. Here we go. Watch out. This is going to be a little bit of a rugged landing. Yo, there we are. And I'm going to take us back to now, if you don't mind. Right there. And we're facing south. And just in case you don't know, if you don't trust me, I'm kind of looking towards the southern part of the sky. So this is really what's in the sky right now. Now I'm going to just move us backwards just a bit because I want to actually go over to the east. Alicia is going to show you this part of the sky a little bit later, but I want to show you the motion of the sky. Remember the spin of the Earth? Remember sort of that is what plants us on the Earth, what directs our attention, what focuses up towards a certain part of the sky. And if I move forward in time a little bit, you see this happening. So I'm just moving just a little bit fast. We're going about 3 minutes every second here in this particular movement. I can put trails on so you can sort of see what happens to those stars. And you can see what's going on here is they're rising from the east and going up at a slight angle. The angle is there because that is represented by our latitude. If you and I were watching this scene and we were exactly at the equator, those stars would rise in the east and go straight up into the sky. But the fact is we're not at the equator. We have a latitude of our own. We're 33 degrees north of the equator, about a third of the way towards the North Pole. And what happens then as we're spinning, right? We like to say the stars are rising in the east. I sometimes like to say that we're spinning around towards the east and exposing the eastern part of the sky. Both of those ways to think about that work, but that's really how this works. And then if we turned around and watched the west, I won't take the time to do that, but exactly the opposite would happen. Those stars would be moving down towards the Earth, and they'd be moving in an angle, and the angle is dictated by your latitude on Earth. Remember, we're on a ball, you know. And so let me just move towards the north. I think this will take me up there. And I wanted to show you something here. That latitude matters here as well. And so I'm going to just point out real quick. This is the North Star right there. And I'm going to start time again. We'll sort of like do the same thing. But look at the characterization of these stars. Look what they're doing now. They're not rising like they do in the east from the thing. When we look directly north, the sky seems to be moving around like a giant clock. And this is a really, really good place to observe and a really good place to sort of think about the movement of the Earth. I do a program up in northern Arizona every year. We do most years when we skip for COVID, but we have all our students out on a football field and we're out under a beautiful night sky. And over the course of 30 minutes, 45 minutes, an hour, a single presentation, everybody gets the experience of actually seeing this happen. They're actually seeing the spin of the Earth reflected in the sky. We call this motion circumpolar. And what that means, let me put the trails on. You'll recognize this, right? So this is some astrophotographers love to do this. They take a camera out there and they put it on the sky and they just sort of like open up the frame and you can see the motion of the stars. Look at how beautiful and graceful that is. So whereas in the east, the stars rise, in the west, the stars set. But when you're looking at the north, they don't set. There's an area of the sky that is always above the horizon. And that, again, speaks to our relationship with the sky based on where we are on Earth. This North Star happens to be 33.5 degrees above the horizon. If we were to do this exact same scene from Salt Lake City or up by the Canadian border, this star would be higher and more of the stars in your night sky would be circumpolar. There would be more of the sky that never sets, that would always be available to you. And just the opposite is true too. If you go down to Mexico or down to the equator, this North Star gets closer and closer and closer and closer to the horizon until less of the sky is circumpolar. Then there's something exactly opposite going on in the south. So for every star in this circle that you can see continuously all night and all year, if you look towards the south, there's a huge part of the sky that never rises. So the further you are north of the equator into the northern part of the sky, the more of the southern part of the sky we just lose. It isn't available to us. So there's probably some travel in your future. If you haven't gone to Australia, down to Argentina or South Africa or something like that, there's a whole new sky down there and it's ready for you to go explore. So this is really sort of the things, the relationship between time and your location and some of the things I wanted to talk about. Let me just do another little thing here. I'm going to turn on just the stick figures that make the constellation the Big Dipper. Here's the Little Dipper right here. The Big Dipper is going to sweep down, just kind of graze across the bottom. But remember, there's two motions. There is the 24-hour day. And so if I were to go, let's say, I'm just going to go ahead 2 hours. 1, 2. And I'm going to do it in 5 seconds. Okay, so this is how much time or how much movement there is in the Big Dipper. If you were to go out right after the show at 8 and then go right out and then watch it until about 10 o'clock in the evening, you're going to find out that there's that much movement in the Big Dipper. That's how far it moves in 2 hours. Let me go back because I'm going to set up another scene. And get back where we started. Now, instead of going ahead 2 hours watching your evening sky turn, I'm going to go ahead 1 month, and I'll do it in 5 seconds. Watch what happens. This should look familiar. This is the same thing. So not only do you have a motion in the sky and a movement of the stars and the star patterns in an evening, right, from dark to dark, right, dark to light all night long, there's this big, huge clock turning, that 24-hour clock that's moving those stars across the sky. But because of that movement around the sun, the start positions of these things change just a little tiny bit every day. Let me show you one day. I just got to pop forward one day. Watch closely. Watch what happens to the Big Dipper. Here you go. Oop, just like that. It's almost not noticeable. This is not the kind of thing you're going to watch a day after day after day and sort of like see a big difference. But if you get to know the night sky, if you start watching these things and start watching the constellations, get to know them and follow them during an evening or during a season or during part of the year, you're going to see this motion and you're going to be able to sort of really kind of connect to how this stuff is working and how it's going. There's some other things I just wanted to kind of talk about is that you know, like my image from the very beginning here, where there's like a dome over your head. We can look at that sky like a dome, and there is a coordinate system attached to that. And all of these stars have addresses, and their addresses relate to that sidereal time. So a star is going to have a time attached to it, and it's part of its address in the sky. So this star right here is called Doobie, and it's going to be 11 hours and some minutes and some seconds. I don't remember the exact thing. And that means that in sidereal time, in star time, when it's 11 o'clock, this particular star is very high in the sky. And so that's how we sort of map the stars. And that comes from, we call that system right ascension. And it just is an hour marker for the stars. We label their position in the sky by where they are in sidereal time. And so I'm going to just want you to remember that, because I'm going to turn the microphone over to Alicia here in a minute. She's going to show you some real life things that you can look for in your January sky. And then I wanted to show you a little, I downloaded a little sidereal clock. And I want to play it for you, show you how that works, show that very specific relationship between local time, your hour time, your solar time, and star time, because you can actually see it on a clock. Okay, I'm going to stop share here and let Alicia come on board, and then she can share her screen. She's going to show you a little bit about a planetarium program you can use, but more importantly, she's going to give you little assignments and things to go out and look for in the sky. Hi, Alicia, how you doing?
Hey, good. How are you?
I got to tell you something also about Alicia. She also works over at the garden, at the botanical garden, and she's just coming off a huge long run of luminarias, and she's all tired. No, she's ready to go. You're ready for the next step, right? The next event?
Yeah, it's 12 days into the new year. I've had time to sleep. So
And I'm glad you're still with us too.
Oh, me too. You can't get rid of me. All righty. So here we are. I'm going to talk to you about some things that you can see in your night sky tonight. But before I do that, I need to share my screen. And so what I'm going to share now is a program called Stellarium. And Stellarium is a wonderful software that you can either download or you can just run from your browser. I'm just running it from my browser. But this is a similar program to what Rick has or what we have in our theater system at ASU, but this is just a little bit more user-friendly for the everyday person. Okay, so what I'm doing now is sharing our screen, and here we are looking north. And so this is our night sky. Rick kind of showed us a view from the Earth earlier, but what I'm going to do is go ahead and light up our constellations. Oop, I did a constellation art, excuse me. I'm going to light up our constellations. And so here, right here at the tail of our Little Dipper, we have our North Star or Polaris. And so this was, again, that North Star that Rick was talking about, that here in Arizona, we're going to see it at 33 degrees above the horizon. Facing north. And so obviously, depending on where you are, this position may change, but if you're here in Arizona, it should be roughly about 33 degrees. And another wonderful marker to find this is if you find the chair or the throne of Cassiopeia, so like the W, you can see that Polaris falls into this W, or kind of like a cap. So that's one way you can find the North Star, or you can also use the Big Dipper, the two stars that kind of guide you to Polaris or guide you to the North Star, excuse me. So this is our northern part of the sky. And what I'm going to do now is kind of shift gears and look towards the east, because those were constellations, or the North Star, excuse me, Ursa Minor is a constellation that we can see year round. As Rick mentioned, it's circumpolar, so we are constantly going to be seeing it. But if we look east, we're going to see some winter constellations that are now prominent throughout this season. And so the first one, very briefly, I want to talk about are the Gemini Twins. And so these twins are pretty famous. It was Castor and Pollux, and they were fighting in a noble battle. And unfortunately, Castor was killed in battle. And so Pollux, being the wonderful twin brother that he is, pleaded with Zeus to get to bring him back. And so basically what Zeus agreed on was the twins could spend half of their time in the night sky and half of the time on Earth together. And so that was the arrangement that was worked out. And so for years and years, or for centuries, sailors used these constellations to navigate, and they believed that if they found two stars in the Gemini Twins, if they could see two stars on their night, that it would be a good journey for them. So just a little interesting story that goes with this winter constellation that we're able to see the Gemini Twins. And then if we continue looking in the kind of towards the southeast, we're going to see another winter constellation known as Orion. Let me get rid of this screen here. And Orion is, again, a pretty famous constellation. I'm sure all of us have heard of it. And if not, I'm sure most of us have seen it. But there's a lot happening in this constellation. Not only is Orion the story of a famous hunter who was hunting Taurus the bull, But he was a very noble and brave hunter, might I add. And so unfortunately, he was killed when he was stung on the heel by Scorpius, the scorpion. And the gods were so pleased with what they both had accomplished that they put them both on opposite sides of the night sky. So that they wouldn't have to see each other. And so whenever we see Orion in the night sky, we're unable to see Scorpius. And whenever we see Scorpius in the night sky, we're unable to see Orion. But since this is the winter, we are able to see Orion. And there are a couple things that I want us to take note of so that you're able to go outside in your backyards and find Orion later. So the first and one of the easiest way to identify Orion would be that by his belt. So we have these 3 stars here that kind of make up the belt of Orion in which his sword hangs, right? So that's a really common way to see or to identify Orion. But another great option would be to look at Beetlejuice or to look at Rigel. So Rigel is technically the brightest star in the constellation Orion, and it is a blue star, which means it's younger and hotter. And then we have Beetlejuice, which is a red star. It's supermassive red star. And so that one is going to have obviously a red tint to it. So if you're looking out with the naked eye, you should be able to determine between Rigel and Beetlejuice because of that slight color difference, the red being Beetlejuice and the blue star being Rigel. So that's something to keep in mind also when you're looking. And then a really just fun note to remember about Orion is that it's not only stars, it's not only a constellation and a story, but there's also the Orion Nebula within the constellation Orion. And that is a stellar nursery where stars are being born and formed. And so there's just lots to look at in the winter night sky, but specifically we would like you to go out and search for Orion. And with that, there is another way that we can find Orion in the night sky, and that is by using some other stars to help navigate. So Rick had mentioned some other stars that we can look at. So if we go down here, we'll see Sirius, which is the brightest star in our night sky. And then we can also see Procyon. And so between Procyon, Sirius, and Rigel, Beetlejuice. Yes, Beetlejuice. Between Procyon, Beetlejuice, and Sirius, these 3 stars form what we call an asterism called the Winter Triangle. And so an asterism is just a fun term for like a constellation within constellations. But those 3 very bright stars will help you to identify, 1, the Winter Triangle, but 2, will help you to identify the constellation Orion. And with all of that being said, that are those are a couple of constellations that you can look for in our night sky. Especially.
Can you leave this up for just a second?
Absolutely.
I want to ask you a question. So when I was talking about sort of the stars in the night sky, and I also mentioned what's observable, what you can actually go out and see. And one of the things Alicia touched on is those colors, right? So you can see relative brightness, and the brightest stars in the brightest part of the sky are just appearing on our horizon. That's why we wanted to introduce you to this eastern part of the sky, because here's some things you can look for. And boy, they're really easy to find. And then remember my motion, right? These are going to be with us for several months as they get a little higher and higher and higher every single day until they cross over the sky. So we're going to be talking about these a lot for the next couple of years. So brightness, but you can also see these relationships, right? So relative brightness, relative color, and those are the things to really start looking for. So, I always ask people, especially students, and say, okay, take a look and then kind of describe what you saw and then take a look again. And I know that you can find actually a couple of extra things, something you didn't notice the first time around. So the last thing, Alicia, if you wouldn't mind just pushing on a star and just kind of touch a star like Rigel or somebody, Beetlejuice. And remember I was talking about right ascension and declination, right ascension over there. Alicia is pointing it out to you. So see how that's actually marked in hours. So the address of Beetlejuice is actually 5 hours, 37 minutes, and 35 seconds. That stays with Beetlejuice for time. That's it. That's its address. And if you're looking at sidereal time, the local sidereal time, at that particular time in sidereal time, it will be crossing your horizon. And so if I have time before we sort of finish the program, I'm going to show you a little clock you can download, and it'll show you the relationship between sidereal time and the others. So let's drop it there. Thank you very much, Alicia. That's exactly perfect. So you sort of know, if you've been with us before, we are very good about giving you assignments. We don't expect you just to not do anything between now and the next time we see you 2 Wednesdays from now. You've got an assignment. You've got to go do something. You've got to go look for these stars that Alicia showed you in the next guy.
We're going to quiz you on it. So
we're going to quiz you. So let's take a little poll break and see if maybe Alex has some questions for us. And I think there's a poll. We got an audience poll, right? Excellent. Okay.
Poll. Let's see here. I'm trying to find the polls, and actually I don't see them. I'm wondering if I need more Zoom privileges.
I need to promote you. All right.
That's all righty. I'm going to go ahead and watch this poll now. Thank you, Kim. See, that's why we keep her here. She's just wonderful. Okay, so I've launched this first poll, and that says, did you catch Santa dropping off your presents while watching the Webb telescope launch on December 25th? Yes or no? So go ahead and cast your votes. Let us know if you were up with Santa. And while you're voting, Alex is going to take some questions, I believe.
Let me just say an answer to that question. Yes, because the James Webb launch was my present. Yes, we actually do have a really good question kind of relating to Orion and all these stars. Sri, I hope I'm pronouncing that right. I might not. How are these stars named? Also, the stories about Orion and the twins, is it real or legends from folklore? Great question.
Yeah, I can take the twins and the Orion questions. So these are based out of Greek mythology. So they have been stories that have been told for years and years and years and years, or centuries better have it. So we cannot say that they are real, but they're mythology that has been passed down for centuries. So, yes.
But I believe that there's a cultural way to look at the night sky, and I believe that it's really sort of been kind of infused in the way we've developed as civilizations and things like that. So I love star lore. I love the stories because they were meaningful to somebody. They wouldn't have been passed down for centuries if they didn't mean something. But of course, there's a science way to look at the universe and all that stuff. But the naming of stars is kind of interesting. So I'll take it real quick, because stars can have many, many, many names. So when we talk about Beetlejuice, Rigel, Procyon, or something like that, those are called proper names. And those are ones that were adopted really, really early on. That's the other thing about astronomy, is we never get rid of things. So if somebody said this was this, then we tend to keep it. But then there's also there's a catalog designations, and the one that for the brightest stars that is the main one we've used is called the Struve designation. It was designed by a guy named Struve, and what he did is he used a Greek letter of the alphabet starting with A, and the constellation. So the brightest star in the constellation is Alpha, and then the constellation name, and in Latin it means the alpha star belonging to. So, and it's a genitive. In Latin, Orion, the genitive is Orionis. So we say Alpha Orionis is the alpha star belonging to Orion. There's also a beta star belonging to Orion and all of that stuff. So those are designations. And then numerous catalogs have come since. And so there's numbers, there's designations, there's letters, there's things. Some stars could probably have 10 or 12 different designations, catalog and whatever. So your brightest ones and the ones that have mythology are going to have a proper name. The brightest ones are also going to have that Greek alphabet Struve designation, and then there's also the later catalogs that came along. So that's it. Why don't you close that poll, and then we'll get on with the next part.
It looks like most of us slept in that day, but 33% of us saw it. So 33% were with us.
I was there. It was amazing. It was really a thrill. I know you had to get up at 5:30 in the morning to do it, but it really was sort of somewhere
It
between
was fun
opening.
spending Christmas with you.
I know we all spent Christmas together, and also Dr. Windhorst is one of the principal investigators of, and it was a science developer of the whole space project, and also has some telescope time on Webb. So, and he's one of our own. It's just really fun to just get into the enthusiasm about this mission, how successful that was, watching the launch and all that stuff. So, with that, I'm actually going to turn that over to Alex because he's actually going to give you an update on what happened and how it happened and all that. So Alex, welcome aboard. And before you start, can you tell people how you're associated with the project?
Yes, gladly. So like Rick mentioned, Dr. Roger Windhorst, who was there, if you watched the ASU live launch, he's been a big part of the development and science done by the NASA Hubble telescope, and now it's kind of next step, the James Webb Space Telescope. So he's been a big part of both of these missions, and he's continuing to be a big part. He's very connected to the Space Telescope Science Institute, which is the organization that actually operates and runs these telescopes once they get into space. So he's been a big part of that, and I've been lucky enough to been working with him in the research I've been doing for the past 2.5 years. So he's been very involved with that. But let's talk about James Webb. It finally launched. The impossible kind of happened. Everyone thought it was going to it might get delayed more than it kind of did, but it launched the morning of December 25th from Kourou, French Guiana, down in South America. There's the launch right there on that video you can see. It was a very successful launch, in fact. So it launched on the Orion 5 rocket. The rocket did a wonderful job. In fact, it did such a good job that it actually almost doubled James Webb's expected mission lifetime because it launched so well that James Webb had a lot of extra fuel left over. And so now NASA's predicting that it'll be able to orbit where it's orbiting, you can see right now with the Earth at the Lagrange point, for even longer and be able to even perform more science for longer periods of time. But at the beginning of the slide, James Webb is actually now fully deployed. It launched in kind of a compact state so that it could fit on the rocket. This is the actual live video feed of it disconnecting from the rocket stage and floating off on its own. That's how the telescope, it's kind of all folded up. You're looking at the base of it right now. And so actually the first thing you could see James Webb do was actually deploy this kind of solar shield right there. That's actually a solar panel that helps power it when it goes to orbit its destination past the moon. But there's a whole bunch of things it has to do. There are actually over 344 points, what we call points of failure in the telescope, which means that there are 344 things that can go wrong. And so for people working on this mission and people who are whose careers are very reliant on this telescope working, that's very nerve-wracking. But this is the deployment process. The first thing that goes, this is a little bit sped up, but this is the solar panel deploying. That gives the telescope power. And as it's flying out to the moon, it adjusts its position, and it begins deploying various instruments to help communicate with Earth and also begin to take science data. The first thing it does is it deploys this kind of antenna, which actually allows it to communicate with Earth and for us to communicate with it so we can make sure that everything's going well as it's deploying. Then you'll see these two big panels unfold. These are the kind of encapsulating panels that hold the solar shield, the big panels that keep the telescope cool and covered from sunlight. There's another one of the solar panels. And so you'll see that these kind of peel away, and then the solar shield will deploy from the two arms that then extend off of the side. Now, this solar shield is very important because the thing is, James Webb is an infrared telescope, so it doesn't use visible light like Hubble does. It doesn't see what our eyes see. It's using infrared. Now, infrared's also, we can also see it in the form of heat. So infrared cameras measure heat. James Webb is kind of an infrared camera, so it's really sensitive to heat, and that means it has to be really, really cold if we want to see really far into the universe. So we need to face it away from the sun, we need to face away from the Earth and the moon, so none of that light and heat gets reflected back, and it needs to be really, really cold. So this telescope puts it at negative hundreds of degrees Celsius to make it really, really cold, where the other side is actually pretty warm. And now you'll see the main things deploying, these mirrors deploying. You saw the main secondary mirror kind of unfold its big arm and lock in place. And then the two secondary mirrors, or the two primary mirror sides fold out, and that becomes the main mirror that James Webb sees out of. You can also see the radiator expands at the back. That's another way to get heat off of the telescope where all the instruments are, and that actually deflects it away from the mirror so that we don't have any interference there. But this entire process has been completed. James Webb is fully deployed, and that means all those 344 points of failure, they've kind of been knocked out. But it's 5 months until we start getting images, and that's because, one, James Webb still has to get to the point where it orbits. It still has to get past the moon to that Lagrange point, these stable orbits, points of gravitation that move around with the Earth around the sun. And also it has to do a lot of calibrating and testing and making sure that everything's operating. One of the main things that's going to be starting pretty soon is all these individual hexagons can move on their own. And right now they're in a position where they're all locked in place so they don't get jostled around for launch and for this deployment. But now they actually need to move back to where they can start actually taking observations. They need to move into one kind of uniform mirror, which is essentially it becomes. And so these things have to move within accuracies of tens of nanometers. So that's like molecular scale. They have to move with such precise measurements so that we can get this really large, powerful, very smooth mirror that'll then begin taking some of the farthest and most, the earliest images of the universe we've ever seen. But at least for most people, the scary part's done. The solar shield, these really thin sheets of thermal material have been tensioned and have been unfolded, and they haven't ripped, which is good. We have 5 of them because we kind of are trying to, in case one of them did have a rip or a problem, then we'd still have some left. But actually, all of them deployed successfully. The mirror's deployed successfully, and so James Webb is on its path to, expanding our understanding of the universe, searching for exoplanets, and doing the next step in science and observation of our universe. And it's going really well. And so for myself, and of course for all the people that worked on James Webb and all the people who will work with James Webb, it's a very exciting achievement. And we're looking forward to in 5 months when we'll start getting those first images back. And you can be sure that we'll have a lot to talk about it then when that all happens. So hopefully, fingers crossed, everything from now on goes just as well as it's been going. And we'll see those beautiful pictures in 5 months. That's the James Webb update. We hope to get many more in the future, and so that's just the excitement of the kind of the year, in my opinion.
Alex, it was excellent report. You can tell you're enthusiastic about this.
Oh yeah, I can't help it. It's yeah. I mean, I was such a fanboy for Hubble, and this is just. Oh, it's just incredibly exciting.
And how fortunate that you are in the stage of education that you are and attached to this thing. I think it's a great story. So good job. And for the audience, we'll be watching these milestones. And so as different things happen, so does the science, and we'll give people updates as we go out. And when there's an opportunity to get one of the researchers or another postdoc or a Dr. Windhorst online, we'll have some interviews. There'll be definitely ways for you to engage with this telescope and what we're learning along the way, for sure. Mm-hmm. So very exciting. That was really great.
Thank you. Yeah,
excellent.
Very exciting.
All right, I'm going to share screen real quick. For those of you that watch kind of regularly, you know that I like this little thing. I sort of started calling the segment Planet Watch, because there was a lot of activity going on in the fall. We watched Venus and Saturn and Jupiter, and it just hung out there and did a show for us for really quite a long time. What I'm going to just show you here, what I'd like to do is just kind of like orient us into the planets. This is where they are right now. Let me just double check. Nope, this is where they are 2 days from now. Let me just go to now, just so you see it. And reorient it just a little bit. And so what's happening here, I'm going to try to get this flat. There it is. And what I'm going to do is I'm just going to size up these planets just a little bit so we can see them better. Let me just turn that radius off for a moment. And what I'd like to do is show you the relationship of where all this stuff is in their orbits, and then kind of give you an idea of what's happening in the night sky. So what you see here is Venus. The planet Venus is almost right in between us and the sun. So in the last week or so, it passed between us. We call that an inferior conjunction. And that's one of the times in its orbit we can't see it. It's just absolutely buried in the blinding light of the sun. If I draw this line over here, things that are on this side of the page, right, are things that are visible to you in the morning. And things that are on the other Jupiter side of the page. The left-hand side are things that are observable in the evening. And so you can see that we are still well positioned to see Jupiter. It is very high in the sky. It's very bright. So Alicia had you looking towards the southeast. If you look towards the southwest, the bright thing is is Jupiter, and it's going to be with us for months. It's going to take it a little while. Remember that we're both moving. The planets are moving and the Earth is moving. So if I set this up a little bit, Saturn is just about to disappear. So I didn't look at it this week. 3 days ago, I could still pick it out, but it's way dimmer than Jupiter. It's way further away than Jupiter, and it's way closer towards the glare of the sun. So we're just about to that point where we're going to go behind the sun and Saturn will be on the other side and we'll lose it. And then, of course, as we move around, Saturn will also be a warning object. But large and in charge in the morning, if you're so inclined. With classes starting, I've been getting up before dawn and going out. I notice Mars is up there. It's really easy to see. It's over in this direction, and that will just become more visible because as the Earth moves in this direction, we'll come around behind the sun. We move faster than Mars. So over the course of the next several months, we'll just sort of start catching up. By the end of the year, by October, Mars will be really bright. We'll have one of those conjunctions where Mars is just exactly opposite us and the sun. So we'll follow this periodically. We like to do it. We like to make this part of our program. So aside from what Alicia assigned you to go look at, I'm just going to have you just go out and check out. Look towards the southwest. You'll see that very, very bright object. That's Jupiter. And then I also like to point out, just watch for the new moon and like the days after a new moon, and then maybe second, third, fourth, fifth day. And you'll see the moon just sort of climb up every night and go past Jupiter. It's actually not, last year we were timed, the new moons in our program happened to happen around the same time. Now we're off cycle, so I'm going to depend on you to watch for that yourself and see what happens. But that is, that's your planet watch. I am going to turn the microphone back over. We've got, I think, another quick poll and then some current events that you got to know about, and then I'll be back to wrap up after that. All right, thank you guys.
Thank you, Rick. I'm going to go ahead and launch our next poll. And that poll is, does your New Year's resolution include more stargazing? We want to know. And there is a right answer. So maybe while we're answering this poll, if Alex wants to hop on and take a question from the Q&A, if possible, or if not, we can just.
Yes, so I've been typing away at some answers in chat, but I'll kind of reiterate because I think there's some really good ones. Steven actually asked how durable the mirrors of JWST are, and also brings up the possibility of micrometeorites, which a lot of people are really worried about, and that's a pretty reasonable thing because you think these little small rocks that are traveling at hundreds of miles per hour, they hit a telescope, they have a good chance of breaking it. Well, I can kind of reassure anyone who has that worry that where James Webb is positioned, the risk of being struck by many objects is pretty low as it is. But also, James Webb, for the most part, has been designed with a lot of redundancies, like with the the kind of solar shield, and has been made with very durable equipment to prevent any damage from being done. So the mirrors, even though they're coated with gold, they're actually made of beryllium. So it's a really strong, lightweight metal. And so if for some rare occurrence a micrometeorite were to hit the mirrors, the damage would be very minimal, if hardly at all. But the risk of James Webb being damaged where it is very low. So luckily that worry is, the team isn't too worried about that. Luckily, I wouldn't want to send it maybe like in the asteroid belt, but even in the asteroid belt, it's not like Star Wars where you have a bunch of them clumped together. They're still pretty far apart. So the risk even there is pretty low, but luckily where James Webb is, it's good.
I think I too saw a presentation. It's anticipated. I think there will be some degradation of those mirrors over time. I think little things are going to hit, but it doesn't ruin the whole thing, right? So there will be little sort of marks and things like that, but they're discernible and it's easy to work around them. And all that stuff. So redundancy was the key. And it really has a 5-year primary mission. But if I remember right, they have enough fuel to make that last more like 10 years or 11 years. If I remember the story
And
correctly.
that was another question we got from Jonathan. Yeah, the minimum is 5 years. That was the minimum. And now they're saying that with the great launch that happened and how much fuel we were able to save, it is significant, quote unquote, significantly greater than 10 years, which was kind of the max.
Right.
So
Yeah.
it ended up being even better than the maximum expectation. So that's incredibly exciting. And that was a really good job from the rocket and the weather and the Earth and everything. It was just a good
Well,
team
I
effort.
guess it was worth the wait then, right, Alex?
Yes. Yeah, it was definitely worth the wait. It had been a long time coming, but I'm just glad I didn't enter 2022 without James Webb in space. I'll just put it at that.
Okay,
What a beautiful
this poll looks great. It really warms my heart. This is really wonderful. Look at that.
Yes,
That's
most
an
of us.
overwhelming majority of people that are going to like watch the night sky. So we'll keep
Absolutely.
you posted. We'll keep you like going. We'll give you things to watch every single week. I think that's super
Yeah.
cool.
You're in the right place. So awesome. Well, Rick, I think I'm next with current events. If you don't
Yep, yep.
mind, I'll go ahead and share my screen now. And it feels so good to share this, everyone. It's been quite a while. But welcome to our current events for this week. I'm going to go ahead and just jump right into it.
Music with that.
I know, Kim, we'll have to work on it after the show. We'll have to get music for sure.
This could be our New Year's resolution music.
Right, stargaze more and get theme music. But speaking of theme, we're going to talk about Themis. So ASU scientists and engineers building the Europa Thermal Emission Imaging System for NASA's Europa Clipper passed a major hurdle today. Recently, they captured their first successful test images, known as their first light images. And so that's very exciting. Here are the first light images. Europa Clipper, again, a NASA-led mission to investigate Jupiter's moon Europa, is planned to launch in October 2024 and arrive at Jupiter in 2030. So a little bit of travel time there, but it will study the icy moon Europa through a series of flybys while in orbit around Jupiter to investigate whether or not it could be habitable or not habitable, excuse me, whether or not it could harbor conditions for sustainable life or suitable for life. So that's something to keep in mind. Very exciting news. Make sure you're checking back with ASU to see how our instrument's doing. And here it is, 3 images that were taken. So this first image, the top one was taken at 12:40 p.m. The second image was taken at 4:40 p.m. and then the third image was taken at 6:20 p.m. And so this is really important because it's the same scene 3 times a day. So throughout the different heat temperatures throughout the day and different conditions, we were testing our Themis instrument and it was successful. So keep an eye out. Yeah, it looks like it works. Keep an eye out for any news as to when that's going to be shipped out and ready to be placed on the Europa mission. So with that, I think that's all my current events.
We've been watching this being built in one of the clean rooms right off of the lobby, in the main lobby in our building. And there's these big, huge windows and you can see people operating in there. And they've been working on this for, oh, goodness sakes, years. So when I saw this little report and they're taking it out of this protected room where there's no dust, there's no anything, and they take it up to the roof of our building, I thought, oh, this is really amazing. I've never heard of such a thing. So but they did it. They took the images they need. Yeah, there it is. So these guys, they're all in there. I mean, look at this. They're in their bunny suits. They have this stuff. They wear little feet things and beard things, and no dust. And then there it is on the roof of the building. I think that's really well. They know what they're doing, right?
I'm just glad I'm not moving it.
Good.
A lot of pressure.
All right, thanks. Hey, let me do something of a wrap up here, if you don't mind. Oh, I think there was one. There's an event we wanted to announce. Yeah. So if Kim, can you just tell everybody about it real quick, and I'll get ready. I'm going to share a screen for the next part here.
Sure. So next Friday evening at Sun Devil Stadium, we are going to be ASU 360 Community Union is going to be hosting movies on the field. The movie will be Dune. And I will throw the link in here to register for that. And also you have an opportunity to ask an astronaut question.
Sorry about that. My fault.
It's okay. So if you want to ask our Explorer in Residence, Katie Coleman, a question, you'll have an opportunity to do that as well. And I will put those links here in the chat for everyone. And if you're not doing anything, I say come on down to ASU next Friday evening and catch the movie Dune. And
Doing it on the football field.
yeah, it sounds like it's gonna be fun. So I'll be there. So I said stop by and say hello.
Hey, I just wanted to kind of just do a little wrap up, just to remind people that we love keeping people sort of in a position where they can kind of just be re-engaging with what I kind of call the meaningful part of astronomy. It's that part that we get to go experience, we get to see those things that we get to do. And so a while ago, I kind of put together a presentation just sort of about time. It was just, kind of the idea was to kind of just see what it's going to take for us to reconnect ourselves and what happens. And the time conversation got a little bit depressing, right? So in this particular scene, you see sort of that bucolic, that kind of farm thing, that agricultural life that we used to live as a civilization, for centuries, for millennia. We've been kind of attached to nature through the nurturing of animals and the growing of crops and the finding of herds and those things that are absolutely tied to the cycles of the earth moving around the sun. We didn't have clocks back then because the cows woke you up because they needed to be milked, and the rooster woke you up, and the sun woke you up, and all of those things. You didn't need a clock to get about your day. You knew what to do because nature was showing you the way. And then, of course, now today, I mean, how many of us are just kind of like just wrapped in our hourly schedules, and we have alarm clocks, and we have to be at a certain place at a certain time, and we allocate our time in a very, very different way. We're really, really more connected to the clock than we are these cycles. And so I kind of went through this whole thing, and there is a whole hour-long presentation. There's about sort of time and how that works, and how our clocks have changed, and how we've come to know time, and all of those things. And so at the end of it, I just have to sort of like get something a little bit more empowering. Kind of how do we? Okay, so here's what's happening to us. We're being disconnected. How do we reconnect? And so over the next 5 episodes of Virtual Night Sky, I'm going to touch on one of 5 things. And so the first one is this is how that works, how to reconnect to the real meaning of time. And the first one is fairly easy, and we've already kind of touched on it. And what I invite people to do, and I do this for young audiences, old audiences, just find a part of the sky that you can own. It's okay, the sky's big enough for all of us. So find a little constellation or an asterism or a thing. It can be one of the Greek constellations, or it can be something you invent out of whole cloth. It's a pattern of stars that looks like something to you. Note the time, do it at the time when you're having an annual experience, like your family reunion out by the lake that you do every year, or somebody's birthday, or some sort of meaningful time of you. Attach your part to the sky, attach that meaningful moment to that thing in the sky, and just go back and revisit it every single year. Own it, it's yours, and you will see that it will be absolutely ever faithful. It will always be there when you expect it to be there. It will always be back in the same place because it is there. That's how the system works. That's how our life on Earth attaches to the sky and directs our attention that way. And that's really it. So the first of the 5 things is get into this rhythm, understand the annual rhythm, find a place in the sky, name it, own it, and visit it every single year. Okay, we will be back with you in 2 weeks at the same time. It's a Wednesday. It'll be at 7 o'clock. And we will be continuing our sort of basics about the sky. We're going to talk about the moon and how to observe the moon and why it has such an irregular orbit and what it does in space. That'll be our thing. We'll have a guest speaker about a little moon mission going on. And then also the other things that we do every week. And then I'll share with you thing number 2 that will reconnect you to the meaning of time. Thank you very, very much for joining us. Sorry, we're running a little late because we don't go by clock time. We go by astronomical time. And we'll see you next week. Thank you.